All right, so this video is a practical guide to interpretations in model theory. So let's recall the following. We gave a definition, and it said that, so we're going to let T1 and T2 be theories. Not necessarily of the same signature, equivalently language. And an interpretation of T1 in T2 is a model of T1 in the category of definable sets in T2. So this was also the syntactic category. We denote it with the script T2. Okay, so another way we wrote this was that the models of T1 in C of T2. So this was the interpretations of T1 in T2. Okay, so this was the kind of topos theoretic version here. But the idea is that we're usually going to apply this to structures. So in practice, we apply this definition to structures. Meaning we take T1 to be the theory of some structure S1 and T2 to be the theory of some other structure S2 where the signatures are in no way related. Okay, and then we actually always take these structures to be in sets. Okay, and then we recall that here that the theory of a structure is all the formulas that are true for that particular structure. Okay, so the actual definition is, so here's another definition, is that given two structures, S1 and S2, we say that S1 or S2 interprets S1 if the theory of S2 interprets the theory of S1, meaning that there exists an interpretation. All right. On a practical level, when we're not talking about abstract categorical things, we use the following. Which I think is strictly, so it's different than the definition that topos theorists use. So I'm going to call this definition claim, and I'm just going to use it as a definition. So let A1 be a structure, so a set valued structure for some signature sigma 1, and A2 be a structure for another signature in sets. So an interpretation of A2 in A1 is a morphism of sets I from X to A1, where we have the following. X an interpretation of A1 and A2. Okay, and some power here is definable. So it's just cut out by definable, a definable. It's cut out by using all the symbols. Okay, so it's a definable set. We defined this before. So, and the other thing is that, so for all y in A1 to some m, so some other m, definable, this inverse image, so we take some power of this thing to the mth power, we take the inverse image of this definable set, and this will be contained in x to the nth power, is definable. Okay, so this is the definition of what an interpretation of A1 and A2 is. It's like the inverse image of every definable set is definable. And so this is the practical definition. So I'm saying this is a claim because, okay, this is what occurs in the model theory literature. This is what occurs in the topos theory literature, and I think that they're not strictly the same. So I'm gonna put this as a claim, and maybe someone can clarify this for me in the comments, what the relation between these two things are. I would appreciate that. Anyway, we're gonna work with this definition. And okay, so that's what I wanted to say. So that's why I said it's a claim. But anyway, it doesn't hurt to just say that this is what we're going to be using for our working definition. Okay, so here's a lemma. So if A1 is a structure, and A2 is another structure, and we have a map of sets, and I from X to A1 is a morphism of sets. With let's say X and A2 to the n definable, then this is an interpretation. I is an interpretation of A1 in A2, if and only if the inverse image of graphs of functions, graphs of function symbols for sigma 1, relations for sigma 1, and the diagonal if all of these things, the inverse image of all of these things here are definable sets. Okay, so the proof idea is that all definable sets are built from these basic operations. And so you do kind of an inductive thing. So I'll link to the part where we define definable sets so you can get an idea of what I'm talking about. So, okay, so that's the basic layout. And now I want to talk about how this is used in practice. So, how to use this, which is the point of the video. So let me give an example. Well, I just want to give an example of how you check these things here. So how do we check that the inverse image of graphs and relations and the diagonal are definable sets and what this actually means? So so here's the example. Oh, let's see. Here we go. This is the example. And so let's look at f, a function symbol, for A1. Okay, what's that? And this means for the signature of A1, which we called sigma 1. Okay, so then gamma of f here, so this is the set of xy in A1 squared such that f of x is equal to y. So this is the definition of the graph. Okay. So to take its inverse image, well, this is in a tuple, so we need to take the inverse image of the product here. Okay. And then we do the inverse image of this. So this is the set of, let's say, AB in x squared. So here I've kind of fixed an interpretation to A1 here. So this is a subset of A2 squared here. Or let's say a to the n, because x would say that, so I guess in before we said that x was in, so here, like here, we said x is in a2 to the n. Okay, so whatever. Okay, so we have this, a2 to the n. And now, okay, so maybe it's bad that I'm not redoing notation every time, but hopefully you get what I'm saying. You smell what I'm stepping in here. So B, this is in gamma of f. Okay, and so this is the same thing as saying that, I'm just going to write it down again. This is a set of AB and x squared such that f of I of A is equal to I of B. Notice that, I should also notice that this thing is just a map of sets. It has nothing to do with definability. It can be something as crazy as you want, right? It's not like a definable function or anything, okay? So, and all it is saying this, okay? So, what you're really checking here is you're really saying that this dude here, so what we really check is that this thing f of I of A is equal to I of B is if and only if, and then we have like some definable expression here. Some definable, what was it doing? DFBL formula. Okay, so we're looking for this thing to be first order. That's the idea. Okay, so we look for this thing to be first order in A2. Okay, and it's going to be first order in A and B are subject to the fact that they are in X. Okay, so to get things rolling, to kind of make this more concrete, let's look at the particular example of monoids. So we're going to do an example. Okay, so that was an example where I just showed you what it meant for the inverse image of the graph of a function to be definable. Now, I want to talk about monoids. So the claim here is that, so let M be a monoid, be an additive monoid. Okay, So what I want to say is that the statement that I want to make is that M group, so this is the groupification of M, is interpretable in M. Okay, so what does this mean? So here, so what's involved here? So M is really, so what do we have? So the signature of M. So sigma. So let's see what this is. So A2. So what are we doing? We're going to do it. Let me go back to the notation here. So we're interpreting A1 in A2. Okay, so in our example, A2 is going to be M. Okay, so this is a structure for sigma 1 in sets. Okay, and sigma 1 has one sort, so I'm just going to write the constant symbol. So there's a constant symbol 0 and then plus. Okay, A1, okay, so this is M group. This is the groupification. So this is a structure for a different signature. Sigma 2, we have 0 plus, and now we have a minus. Okay, so we have this additive inverse. Okay, so this is an additive monoid. It happens to satisfy extra axioms, but we don't really care right now. Okay, so we're going to show that that we can actually construct the group in this normal language here, and it's something that you'd expect. Okay, so so the idea here is that I'm going to write down the interpretation. Here's the interpretation. The interpretation is the map I. Okay, so now over here we're going to have the group. Okay, and then we want the inverse image of all of these things to be this. So we're going to do M cross M. So this is kind of like so we need to talk about negative things. And let me show you the map. So Pn. So these are just going to be two elements in this additive monoid. And now in the group we can subtract things. So I'm going to do P minus N. So P and N are supposed to be like positive and negative here. Okay, and like I said from the lemma, where's this lemma? So there's this lemma here. So this, let me say this lemma here. So we need to check these things here. Okay, so that the function symbols, relations, and operations. So what are the function symbols? So the function symbols are, so we only need, there's no relation symbols except for the equality relation. But that was kind of included before. So let's check the function symbols. So we need to check that okay, now this is I3 inverse of gamma of plus is definable. Okay, so this is the first thing that we need to check. Okay, so okay, we need to check this one. We need to check the equality. Let's just do the plus one first. Okay, or let's see. This one's okay. Let me just write down. We need to check. Let me just write them all down. Okay, so we need to check I2. Oh, this is inverse of so the equality. So let's talk this graph of equality. Maybe that's a bad way of doing it. Sometimes it's just denoted by this diagonal, right? And we need to check, and then the minus operation. So minus is a binary operation, right? So that a single function symbol, it sends positive to a negative number. Gamma of minus is definable. DFBL. Okay, So sometimes I might omit this positive power here because it's easier to do that. Okay, so let's do equality first. So for equality, we're going to say that okay. So we need to check that this expression p prime n prime. So this is definable. Okay, and so it turns out that this expression here is definable because p. This is true if and only if. So what is this? P minus n is equal to p prime minus n prime. Okay, so that's not. This is definable in M group, right? This makes sense. But it turns out that we can make this expression that makes sense. P plus n prime is equal to p prime plus n. Okay, so now this is a definable. This is definable. This is a good formula, a first order formula. In M, okay? And so now this is a definable expression, and maybe to be completely explicit for this one, so inverse of gamma equality here, so this is the set of, here it's P n, P prime, n prime, such that P plus n prime is equal to P prime plus n. Okay, and so this is a definable set. Okay, so this is completely explicit now. All right, so we've checked off the equality. Now I'm going to check off the other ones. Okay, so just to be more, so just to kind of, just to be kind of explicit for this first example. So so how did I do this? So addition. Okay, so here we check that I of p n plus I p prime n prime is equal to I of p prime prime n prime prime. So this is the graph of the addition thing. So you have like x plus y is equal to z, okay, or x prime plus x prime, or x plus x prime plus x prime prime is x plus x prime is equal to x prime prime. Okay, so we have this addition, and all right, so let's write this out. What this means in terms of the interpretation. So this is p minus n plus p prime minus n prime. Here is p prime prime minus n prime prime. Okay, and now we do the exact same thing. So this makes sense in the group, the groupification, and so we can do p plus p prime plus n prime prime is equal to. So this is the same thing as this in M group, but this formula now will make sense in M. Okay, so this is definable. Okay, so we have this addition, and now we can check the inverse. So subtraction, or the negative function. So we have I Pn is equal to I p prime n prime, if and only if here that I Pn is equal to I of n prime p prime, and then we've actually written this out before. So this is the same thing as, well, p minus n is equal to n prime minus p prime, and so this is the same thing as p plus p prime is equal to n plus n prime. So this one, again, this makes sense in M group, and this one makes sense in M. And so now this is the definable formula here. Okay, and that's that. So this we've shown now that that where are we here? So that this is now an interpretation of this structure, which is the groupification in this. So the idea is that you can make statements, first order statements about the groupification of M just by knowing M. Okay, so that's kind of interesting. So here's another example. So let's let A be an integral domain. And then let's let K be the field of fractions of A. Okay, then I from A cross A, and then we'll do this symbol here, to K, given by AB maps to A over B here, is an interpretation. So this is surjective. So here, sigma K, so the signature here is one sort, right? So I'm just going to omit that. So, and then we have plus times, we have the negation operation, the inverse, multiplicative inverse operation, and then 0 and 1. So we don't need to worry about 0 and 1. What we do need to worry about is that so we check that the inverse images of the following graphs here. So this thing plus the graph of multiplication, the graph of the additive inverse, the graph of the multiplicative inverse, and the graph of equality, which is the diagonal, are definable sets in the same way. Okay, so this is kind of the standard procedure. So here's just another example of what you can interpret in another. And now you have that A star, so this is the A and A, such that A is not equal to 0. And this is also definable. Okay, so now this is an example where we have a definable set here. So I want to give another example. So here's an example. So groups with a predicate for membership of a normal subgroup in a normal subgroup, in a particular normal subgroup, interpret the quotient. Interpret the quotient. Okay, so here's what we're going to do. We're going to make two structures. So the S2 is going to be the group. The group is the single sort. It'll have multiplication. It'll have the inverse operation. And then it'll have the identity. And then also we're going to throw in here this predicate, a single predicate for membership in N. So we have this fixed group G and we have a fixed group N. Okay, and then S1 will be this group G mod N with the induced addition and multiplication. So we in this, and then we have the identity too. Okay, so this is the identity of G. This is the identity of G mod N. Okay, and again, this is the multiplication for G mod N, the inverse operation. Okay, so all right, and so we want to interpret in this thing, and so here, the map, the interpretation is given like so. So we'll take this guy, G, and we'll map it to G times N. Okay, so what do we need to check? We need to check that addition or multiplication, the inverse operation, and then equality are defined. So to check that this is an interpretation, we check, okay, so the diagonal, which is the graph of equality, we check the graph of multiplication, the graph of the inverse operation. I should have used S, I guess. And then that's it. Okay, so here let's check the graph of. So here what do we have? So we have I G1 is equal to I G2. Okay, so this is true if and only if G1 n is equal to G2n. This is true if and only if, so this is for equality, by the way. Okay, so this is true if and only if G1 G2 inverse of n is equal to n. Okay, and this is true if and only if G1 G2 inverse is a member here. And so now this is a first order in S2. Okay, so this is this thing. So now we have this membership. So we've supposed that we have this first order definable thing. So if we have this group now, and we can make sense of membership here, we can make sense of equality. Okay, so for multiplication, and multiplication and inversion are similar. Oh. Okay, so we've kind of done these baby examples. So now it's my intention to do some more serious examples, and the two serious examples will be the fundamental theorem of projective geometry and the interpretation of the divisor class group inside a ring of integers for a data domain. All right. Sometimes there are two ways. Sometimes there are two structures you can interpret that give you the same thing. Same thing. Okay, so here's an example. So first structure. So the first structure could be, so let's let A be an integral domain with its usual ring structure. Okay, so, and then we're going to have, we could have this kind of two-sorted structure where we have KAI and this inclusion map here. So we have this other structure here where, okay, implicit in this notation, A has, it's sort, addition, multiplication, negation, 0 and 1. K has its sort, addition, multiplication, negation, multiplicative inverse, 0 and 1. And then there's this function symbol from one to the other, just the inclusion operation. And so in the usual way, we can interpret K, or sorry, this structure, let's call this S, S inside A. So what does this mean? So I guess we have two sorts here. So we need a map K, A here. Okay, and then what would be the surjective map here? So I guess we'd have A cross A, the non-zero elements here, and then A here, where we have here P, Q, let's say R. This goes to P over Q. R. And then you just check that the inverse image of each of these operations here with this I here is well defined. Sorry, is a definable set.